Hi class. So, section 5 is all about mechanical drawings. And I want you guys to start off by following this link and watching this YouTube video about the fundamentals of engineering drawings. So this is a very detailed video. It has a lot of good information and animations. So go ahead and watch that. And that's going to actually cover a lot of what's in this workbook as well. And so I'm going to go over it very briefly before I get started on the mechanical project. Okay, so drawing standards, those often follow drawing conventions, and a lot of companies will have their own set of standards and requirements as well. And so ASME, that is the most common convention in the US, but there is also many other ISO standards that are used internationally. All right, and drawings will often have a title block, and this includes a lot of important information. You might see a revision history table to list any changes to the drawing, and it's going to have some tables and notes to provide additional information as well. All right, and assembly drawings show how different components of an assembly fit together and the relationship between them. So it's usually an isometric view, something like this, and you might have callouts that point to each one, and then you will have drawings that go to each of those separate components. And so because this one has all these balloons, for example, it would have a bill of materials or a BOM that lists those different parts. All right, in detailed drawings, so this will include the primary views that we've talked about previously, including the front, side, and top views. And in the US, we would use third angle projection for that. And so that is a symbol. The symbol for that is a circle with a cone on the right side. So like this. All right, let me go back a little bit. And detailed views, these are used for showing some small details at a larger scale. So it'd be like zoned in or zoomed in. And you might also have sectional views, which is a cross section of some part or component to show the internal details of that component. All right, and so tolerances. No part can be manufactured exactly to the set of specified dimensions, right? There's always got to be some tolerance that will express the acceptable deviation from the nominal size. So tolerances should not be tighter than is necessary because the smaller that tolerance is, the more expensive it will be for that part to be made. And so tolerances will look something, they might look something like this, where it's going to have a plus or minus. It might have a plus or minus in a different value on the top and the bottom, or they might be the same on either side. All right, and so with chained dimensions, these are dimensions that are given sequentially, with each dimension starting from the previous. And this can be useful. We need some evenly spaced features like holes or slots in a row. However, this can result in tolerance stacking. So tolerance stacking refers to the way that the tolerance from one dimension is added to the next, and so this will result in a larger variation in the location of the last feature in the chain. So for example, here's some component, and when it's dimensioned with the chain dimensions, the accumulation of tolerances from surface A to surface B is 0.3. And that is because, let's say right here is where we're starting, you might add or subtract because they add 0.1, another 0.1, and another 0.1. So that's 0.3 in the end. And then baseline or datum dimensions, it measures all the dimensions from a single reference point or datum. So in this case, this here is the datum, and all the dimensions are measured from there independently on their own. So this is very useful for critical dimensions, precise assemblies, or parts that interact with other components, and it prevents tolerance stacking. So in this example, the accumulation from surface A to surface B is zero point 0.2. Because let's say that if this is on the lower end of its tolerance, so it could be 39.9, for example, and then this one might be 110.1. And so between 39.9 and 110.1, that tolerance stacking, that would be zero point 0.2 because this one is on the lower end and this one is above by 0.1. This one would be below by 0.1. All right, and so in this example, though, the accumulation between surface A and surface B is just 0.1, and that is because the tolerance is specified specifically between surface A and surface B. And so if you have a critical component that has a critical dimension, you would want to dimension it something like that. Okay, and then there's a couple of specialized drawings. These are layout control drawings, interface control drawings. We're not going to really deal with these so much, but layout control drawings, that would be for very large systems usually. And interface control drawings, that's just to show the connections between two interfaces. And so our assignments for, or our assignment for this section is just one. It's one large assignment known as the mechanical project. And I'll go ahead and create a separate video for that. Thank you.